Let's get started. All right, guys. So AS Physics. Okay, a bit of an intro. Okay, so in AS Physics, you have three papers: P1, P2, and P3. Okay, P1 is MCQ base, has 40 MCQs, 1 hour. Okay, P2 is theory. Right, it has short and long questions. Okay, calculation stuff. You have to show your working, etc. And this is of a greater weightage, and P3 is practical. Right, this is. I'm assuming you guys know what this is. Right, you guys
Yes,
are
yes.
familiar of all this stuff.
Yes, sir.
Okay, now going on to the topic. And by the way, you guys also know that P2 has a greater weightage than both the other components, the P1 and the P3. And P1 and P3 has equal weightage. Okay? Right, so let's get started. All right, so the topic that we are going to cover today is moments. I'm not starting from chapter 1. Okay, we will do chapter 1, but later on, I'm doing the better chapter today. Okay, because chapter 1 is pretty basic. We can do that anytime. Okay, moments now. All right, by definition, what is moments? Moments is the turning effect of force. And this is something you've done in O-levels as well, like somewhat the turning effect of force is called moments, and the turning effects of force is called moments. And mathematically, if the examiner asks you to define what a moment is, so this is not enough for the definition. Okay, you have to define it mathematically. You have to write it as the product of force, and the perpendicular distance between the line of action of force and the pivot. Okay, I'll explain what this means. Basically, if I have a log over here, okay, this is a log, a wooden piece of wood, a stick, okay, and it's fixed from one end such that it is freely movable. Okay, it can rotate clockwise or anti-clockwise about this fixed pivot. Okay, this is called a pivot. All right, so now if I apply a force over here at this particular point, so now this arrow is representing, this dotted line, this arrow is representing the line of action of force, because this is the point where the force is in action. Okay, this is the point where the force is acting. And the perpendicular distance, perpendicular means at 90 degrees, right? So right perpendicular to this. Okay, so if I were to draw a line over here, okay, forget this. For example, if I were to draw a perpendicular line from over here all the way till this point, so this distance over here, this angle is 90 degrees, right? This is the 90-degree angle, and the green distance, the dotted green distance between this point and this red line, this is perpendicular. This distance is the perpendicular distance from the pivot. So if I were to take the product of this force and this distance, I'll get the moment of this force. Okay, so the moment of this force is the product of force and the perpendicular distance from the line of action of the force to the pivot. Okay, so this is how we can write down the definition of moments mathematically, and this is the formula that we'll use throughout this chapter. Okay, this is an important formula which I assume you guys already know from O-levels. Okay, and
Yes.
is the line of action of force. This is the perpendicular distance between the line of action of force and the pivot. Okay, and this definition comes for approximately 2 marks. Okay, so if you are asked to define what moment is, so this definition over here, the product of force and the perpendicular distance between the line of action of force and the pivot is called the moments. Okay, this is the definition you are supposed to write. Okay, moment is the turning effect of force, but this is not the complete definition for 2 marks. Okay, this is the definition you are supposed to write. This is a definition which is given in the marking schemes as well. All right, and now if you guys, what do you guys think? What will this force do? It will actually cause this log to move in the clockwise direction, right? It will cause it to rotate or to turn in the clockwise direction. So this turning effect, this turning of this force, this turning effect is actually the moments, okay? And this is possible because there is perpendicular distance between the force and the pivot, okay? Now, for example, if this perpendicular distance becomes 0, if this force acts right over here at the pivot, if the force acts at the pivot, okay, if I take this force from here, I pick it up and pass it through this pivot, if the line of action of force passes through the pivot, then in that condition, the value of this distance becomes 0, right? And if the value of the distance becomes 0, then in that case, the turning effect or the moment will also becomes 0. So this is a general rule you guys should remember, that whenever a force passes through a pivot, let it be in this direction or in some other direction, okay? For example, if a force is being applied from the right hand side towards the left hand side, but its line of action of force is still passing through this pivot. So again, there is no perpendicular distance between the pivot and the line of action of force. I told you the perpendicular distance is what really matters for the moments, okay? Or you could just remember it this way, that whenever a force passes through the pivot, its moment is 0, okay? So the force passing through the pivot has 0 moment. Any questions so far?
No.
Guys?
No.
Okay, no question? All right, I'll move on. Okay, and guys, this in our syllabus, we also refer to the moment as torque. Okay, torque and moments in our syllabus are the same thing. So if the examiner asks you to calculate the torque, he's actually asking you to calculate the moment. Okay, no such difference over here. Okay, if I have a uniform plank, uniform means a plank which has its center of gravity at exactly geometrical center of that plank, okay? For example, the length of this plank is 100 centimeters, okay? The length is 100 centimeters, so exactly at 50 centimeters, at exactly middle, at exactly halfway from both the edges, at exactly 50 centimeters, will the weight of this plank act, okay? Such a plank is called a uniform plank, or it can be a log, or can be any stick, okay? As long as it is uniform, its weight will act from the center, okay? So remember this, that its weight will always act from the center, because there are questions relating uniform planks, and we're gonna discuss them in a bit, okay? So this is what uniform really means. Now, if I have this plank, oh, sorry. And it's balanced by a pivot over here, all right? And for example, this is an equilibrium, okay? The plank is resting. It's not going down to the right hand side, nor is it going to the left hand side. And the weight of the plank is, let's say, 50 newtons. And if I ask you to label the weight of the plank, okay, and if, for example, there are several markings on this plank, and the markings go up to 10, from 1 to 10. So what do you guys think? Where will this 50 Newton act? Any suggestions?
5 centimeters.
5. Yes, exactly, 5. To act downwards.
What's center of gravity?
What's center of gravity? We are about to define that in a bit, but I'll just tell you because you've asked. Center of gravity or center of mass. They are In our syllabus, we don't distinguish between them. Okay, center of gravity. Actually, the definition of center of gravity is asked. Okay, center of gravity is the point on a body at which the entire weight appears to act from.
Okay.
So for example, if the entire weight of this plank is 50 newtons, and if its center of gravity is at exactly 5 unit, okay, I've not marked the units, but just assume this to be some imaginary unit. So if it is at exactly 5 unit, then the entire weight, it appears to act from this point only. Okay, it will not act from any other point on this plank, on this ruler. Okay, and now if it's acting downwards, and if this is the two mark over here, so this force, and there is a force and there is perpendicular distance between the pivot and the line of action of force. And in this case, just assume this to be very accurate. 5 minus 2 is 3, right? The distance is 3. Okay, so the moment in this case is gonna be in the clockwise direction, and the clockwise moment is gonna be 50 times 3, 150. Okay, and for example, if these units, these markings were in meters, then it's gonna be Newton meter. Okay, this is gonna be its unit, Newton meter. Or if it were in centimeters, then it would have been Newton centimeters. But guys, in our syllabus, we deal with SI units. Okay, so you have to convert the centimeters to meters in order to calculate the answer in Newton meters. Okay, this is the final SI unit answer that you'll get.
Okay.
This was just an example. Oh my God. Just a moment, guys. Okay. Now, okay, let's move on. Okay, the next thing that we need to deal with is, all right, let me tell you something. Like the clockwise moments. Okay, let me tell you that moments are vectors. Do you guys know what vectors are from your O-levels knowledge? Moments are vector quantities.
They have magnitude and direction.
Yes, they have a magnitude and a direction. They are vector quantities. They have both magnitude and direction. This is what a vector is.
Yes.
There are two possible directions for any moment. Okay, we have clockwise direction, clockwise moments, and we have anti-clockwise moments or counterclockwise moments. Okay, same thing. The clockwise moments are going to act to the right, okay, in the direction of a clock, like this, from the right to downwards, or like this, okay, in the direction of a clock. Okay, this is a clockwise direction, and the anti-clockwise or the counterclockwise will act in the opposite direction to the clockwise moment. And for example, if this is your pivot and I place a mass over here, its weight is going to act downwards and it will produce a clockwise moment. And if I were to place a weight somewhere over here, its mass will act downwards and it will produce a counterclockwise moment. Okay, so this is the difference between clockwise and counterclockwise directions of the two moments. Now, the next important part of this chapter is principles of moment. This is a high yield topic, principles of moments, and has been tested several times. Okay, in fact, almost every question of moments include the principles of moments in it. Okay, so this is something you've done in O levels as well. This is just a quick recap of what you've already done in O levels. Okay, principles of moments. Okay, the thing that's new in here is that principles of moments is the second condition of equilibrium. Second condition of equilibrium. I'll tell you what the first condition is in a bit. Okay, guys, so first of all, what is equilibrium? Anything is in equilibrium if it fulfills the two conditions, okay? Now, it will be clear just in a bit. Okay, the statement of principle of movement says that if an object is in equilibrium, the sum of clockwise moments
are equal to the anti-clockwise.
yes, exactly, the sum of clockwise moments is equal to the sum, okay, to the sum of counterclockwise or anti-clockwise moments. Right, so guys, the important point over here is that I've used the term sum of, okay, so all the moments which are acting in the clockwise direction or all the moments which are acting in the counterclockwise direction, if you have to place an object in equilibrium, they must balance each other out, okay? So mathematically it can be written as sum of moments, sum of clockwise moments is equal to the sum of anti-clockwise moments. So all the moments which are acting in the clockwise moments, clockwise direction must equal the anti-clockwise moments. And in this case, if a system obeys this law or obeys this condition, then it is obeying the second condition of equilibrium. But we cannot be certain whether that object is in equilibrium or not unless it also fulfills the first condition of equilibrium. And we are going to talk about the first condition of equilibrium in a bit. First, let's finish off the second condition of equilibrium. Now, for example, if I have a log over here and placed on top of a pivot, okay, and I have two masses, one mass to the left and other to the right, okay, the mass to the right has a weight of, let's say, 50 newtons, and the distance between this mass and the weight is, let's say, 2 meters, okay? And for example, if this the mass on the left hand side is at a distance of, let's say, 5 meters, and its weight is, let's say, 100, so 20 newtons, okay, yeah. And I claim that this plank is in equilibrium. So to check whether it's in equilibrium or not, what are we going to do? We are going to calculate the clockwise moments and the anti-clockwise moments and see if they are equal. Then this plank is surely in equilibrium. It will not topple. Okay, it will not move. It will not move in the clockwise direction, nor it will move in the anti-clockwise direction. So let's calculate the clockwise moment first. It's 50 into 2, 100 Newton meters, and the counterclockwise moment is 20 into 5.
It's in equilibrium.
It's also 100 Newton meters. And yes, the second condition of equilibrium has been fulfilled. And this log is in equilibrium and it will not topple. Now, if I place another mass of, let's say, 10 newtons at a certain distance, let's say distance of 2 meters, and if I ask you that where should I place a mass of, let's say, 30 newtons, okay, let's say 30 Newton mass is over here. This green block over here represents a 30 Newton mass. Now, to keep this log in equilibrium, where should I place the 30 Newton log? This can easily be calculated by using the law of the principles of moments, okay? First of all, for equilibrium, you guys know that the sum of clockwise moments and the sum of anti-clockwise moments must be equal. Now, to calculate the sum of clockwise moments, what are you going to do? First, identify the forces which are producing a clockwise moment. Is the 50 Newton producing clockwise moment? Yes. Is the 30 Newton also producing a clockwise moment? It is, right?
Yes.
So now, and what about the 10 and 20? No, they are not. They are producing counterclockwise or the anti-clockwise moments. Okay, so the sum of clockwise moments is gonna be the moments which are produced by these two forces. So 30 multiplied by some unknown distance which we need to calculate.
X, we make distance the subject.
Yes, then we'll make it the subject. 30 into x plus 50 multiplied by 2, which is equal to 10 into 2 plus 20 into 5. All right, so sum of clockwise and sum of anti-clockwise moments are equal. Now just calculate the value of x and you'll get the distance for the moment. Right, you have the answer to it? 100, 120 minus 100 equals 30x. Sorry, what's the answer? Isn't it 2 upon 3? 20 times 100. Yeah, it's 2 upon 3 meters. Okay, so we have to place a 30 Newton block at a distance of 0.67 meters or 2 upon 3 meters to the right. Okay, if it is 0.67, right? Right. So this was the second condition of equilibrium or the principles of moment. Okay. Any questions so far in principles of moment? Bilal, Khalid, anyone?
No,
all right. So now the past papers are loaded with example questions. Okay, the past papers are loaded with questions which apply the law of conservation. Sorry, which apply this principles of moments in there. Okay, and this is the basic concept behind it. Okay, nothing new, exactly what's from what you've been doing since O levels. But now let's do something that's new. You guys know what resolution of vectors is? Resolution of vectors.
Yes, sir.
You do? Okay, cool. That makes it easier. Resolution of vectors. But I'll explain it anyways. Okay, guys, resolution of vectors. If I have two vectors, just one vector acting in any random direction, always remember that in our syllabus, we are dealing with two-dimensional vectors, okay? Two-dimensional vectors. Two-dimensional vectors are those vectors which have two components, two perpendicular components. One acts in the y direction or in the direction parallel to the y-axis, and the other acts in the direction parallel to the x-axis. Okay? The component that acts parallel to the x-axis is known as the x component, okay? And the component that acts parallel to the y-axis is known as the y component of the vector. All right? Now, for example, if this angle is theta and this vector that acts is f, okay? So, and if I apply trigonometry over here, can I calculate the length and assume this to be a right angle triangle? Okay, wait, let me draw it a bit more clearly. The x component, it acts parallel to the x-axis. Okay. This is one component of the vector. And the y component acts perpendicularly to the x component. Because you guys know that the x and y axes are perpendicular to one another, right? At 90 degrees to one another. This is the y component, this is the x component, and it has a 90-degree angle. Now let's apply trigonometry to get the values of these components. If I were to calculate the value of this x component, the red component, so can I apply cos? Can I apply cos of theta? Okay, I can apply theta. I'll call this fx and I'll call this fy. So cos of theta is gonna be the adjacent side divided by the hypotenuse. Okay, so adjacent side divided by the hypotenuse. And so now if we make the fx the subject, it becomes f cos of theta, right? And now the shortcut is that always, guys, remember that the side which is adjacent to the angle along which the force is acting, it's always the cos of that angle times that force, okay? F cos of theta. And if you talk about the y component, it's gonna be F sine theta, okay? Applying the same trigonometric ratio, you can apply sine theta on it. Sine theta is gonna be Fy upon F, okay? And so Fy is gonna be F sine of theta. So the y component is gonna be F sine theta, and the x component is F cos theta, okay? And if I were to apply Pythagoras theorem over here, the F square is gonna be the sum of F sine theta squared plus F cos of theta squared. Right? This is Pythagoras theorem. Okay. The hypotenuse equals the square of the other two sides. The square of the hypotenuse equals the square of the base and the height. Well, we don't need to use this formula a lot. Well, we do actually need to use this, but there is no specific question in which the examiner asks you to calculate the force using this formula, but this is where you need to figure it out, and this is what you'll get into practice once you start doing the past papers, okay? Once we get to the past papers, we'll get into the practice of solving using that formula as well. All right, so this was all about resolution of vectors. Now, we are going to use this resolution of vectors over here in moments, okay? Now, how to use it over here? It's very simple. If I have a plank again, okay, a horizontal plank over here, and now it's pivoted somewhere over here, okay? And let's say this time a force acts at a certain angle. Now let's take the distance between, it acts at a particular point, okay, and the distance, okay, it acts, for example, over here at this point at an angle of, let's say, 30 degrees. It's not acting right perpendicularly, but it's acting at an angle of 30 degrees, right? And let's say the component, the value of force is F, and this distance is small d. Now, how to calculate the moment in this case? Well, guys, I told you that moment is the product of force and the perpendicular distance, right? The perpendicular distance. So this means now in this case, the distance is not perpendicular, right? It's at an angle other than 90 degrees. It's at 30 degrees. So we need to calculate a component of force which is perpendicular to this distance. Guys, if I were to split this force into two components, this is going to be the horizontal component, right? A horizontal component. Yes. And if I take another component perpendicular to the horizontal component, it's going to be the vertical component, right? Now, this vertical component, when multiplied with this distance, will give me the moment of this force, rather than this entire force being multiplied with this distance, because this component is acting perpendicularly to the distance. Now let's calculate the value. First of all, guys, if this angle is 30 degrees, so I can say that this angle is also 30 degrees, all right? Alternate angles.
Yes.
Any confusion over here?
No, sir.
All right. If this is 30 degrees and the value of the force is F, so what's gonna be the perpendicular component? It's gonna be F sine of theta.
F sine theta.
Right? F sine of theta. Now, if I were to calculate the moment over here, so the moment is gonna be F sine of theta multiplied by this distance, d. So this is the case when the force is not acting perpendicularly, but is acting at an angle. So you take that component of the force which acts perpendicularly. Now, someone might ask that why are we ignoring the other component? Why are we ignoring the F cos theta component? Well, we are ignoring it because it is actually a component that is okay, I can take this component acting over here, or I can consider this component acting over here, right? Doesn't
Yeah.
matter as long as it's acting at the same point. Okay, so if I were to act it over here, then in that case there is no perpendicular distance. There is no perpendicular distance. Okay, for example, if this is the point where the pivot is placed, okay, if this is the point where the pivot is placed, then the perpendicular distance is going to be 0. Well, let me rephrase my words just a moment. Now, for example, if this is the point, okay, let me make the diagram a bit better. The force actually is not acting at this top, but it is actually passing through this point over here, through this point, or through any point over here. Okay, now in this case only the perpendicular component is taken, whereas the other component, since it is parallel to the distance, okay, this component is parallel to the distance, right? F cos theta is parallel to the perpendicular distance. So this means that the angle between the perpendicular distance and F cos theta is 0, so F cos theta is ignored because its moment is not going to be any. It will have a zero moment. Or you could just assume it to be acting, to be passing through the pivot over here. If this is the pivot, and if you ignore the triangle over here, if this is the pivot over here, so this F cos theta is actually passing through this pivot. It's actually passing through this pivot. Over here. Let's look at it from another angle. Now, if this is the pivot, okay, this is the free moving pivot, and our force acts over here at this point at an angle of 30 degrees. And the distance between the pivot and the line of action of force is this d. So we have to take that component of force which is right perpendicular to this d. Okay, and in this case, if we were to split it into two components, horizontal component and the vertical component, then the distance between the vertical, the product of the vertical component and this distance will give you the moment. Okay, this is 30 degrees and that's the force. This is F sine of 30. This is F cos of 30. This F sine of 30 when is multiplied with the d will give you the moment, whereas F cos of 30 is actually acting over here. Okay, we can translate this vector over here, we can move this vector over here, acting over here at this point. So if we were to extend the line of action of this force, it actually passes through the pivot. And I told you earlier that if whenever a force acts through the pivot, whenever a force passes through the pivot, its moment is going to be 0.
0.
Yes, this moment is 0. Any questions so far of resolution of
No, sir.
right? This was a new concept, okay, relatively new concept for you guys, right? So this is pretty much of the first half of the chapter, and guys, you can even generalize it, okay, if you know the angle, if you know this. Sorry about this. All right, so if this is a plank over here, okay, and this is the pivot, and you know the angle between the force and the pivot, you know the angle between the force and the pivot, you could just take F sine of that angle multiplied by the perpendicular distance multiplied by the distance between the pivot and the force, because it actually means the same thing. It is actually this stuff that we get this general formula for. Okay. Well, the concepts will get cleared even further once we get on to the past paper practice. Now, moving forward, we've discussed the second condition of equilibrium. Now discussing the first condition of equilibrium. First condition of equilibrium is also not new. First condition of equilibrium is with respect to forces. Okay, so whenever the net force is zero, whenever the net force is zero, that object is in equilibrium. Or if you want to write it in wording, it's going to be an object is in equilibrium
when the forces are balanced.
Yes, when the forces are balanced, or you could say that when the sum of all
No
forces,
forces applied.
sum of all forces is zero.
Yeah.
All right. So, for example, if I have another plank over here, okay, and we have certain forces acting upwards and a certain force acting downwards. Let's say 50 Newton is acting downwards, 20 Newton is acting upwards, and 10 Newtons is also acting upwards. So is this plank in equilibrium or not? The forces which act in the upward direction are 30, forces acting in the downward direction are 50.
No.
50 minus 30 is 20. 20 Newton is the resultant force. The resultant
20
force and the
Newton
net force
downwards.
is not zero. So yes, it is not in equilibrium. Okay, not in equilibrium because the net force is not zero. So the two conditions of equilibrium. First condition is the net F net must be zero.
Yes.
Second condition is the net torque or the net moment must be zero. If both the conditions are satisfied, only in that condition that object is in equilibrium.
Yes.
Okay, that object is in equilibrium. If one is satisfied but the other is not, then the object is not in equilibrium. Okay, I'll give you an example of that as well now. For example, if I have a plank over here, okay, and a force acts right over here at 10 newtons, force acts downwards, and a 10 Newton force acts upwards. Now guys, is this plank is in equilibrium? Apply both the conditions that you've just seen. The first condition, according to the first condition, the forces are acting upwards and downwards.
Yes,
so
balanced.
Zero, yes. The first condition is satisfied. What about the second condition? Will there be any torque produced in this plank? This force will actually cause a counterclockwise movement, and this force will cause a clockwise, both the forces will cause counterclockwise movements, right? Both the forces are causing counterclockwise movement, so the torque net is not zero. So this object is not equilibrium. Okay?
Not in
Equilibrium. All right, so this was one example. Now let's do another example. There is a plank, okay, and oops. Okay, and this is the pivot. Now a force acts downwards of, let's say, 5 newtons, okay, and this force is balanced by some other force over here, say 50 newtons maybe. Okay, 50 multiplied by this distance might be 2 meters, and this force is at a distance of, let's say, 20 meters. Okay, just assuming these values. Okay, these are not the true values, of course.
Yes.
Now, and the weight, okay, let's not take this 20, let's assume this to be, or just forget the numbers. I'll first give you a general example and then we'll go on to the numbers. Now this is a this is a plank, and this is the pivot. Guys, is there any force between this pivot and this plank? Any force acting over here? You guys remember what normal reaction force was?
Contact force.
Yes, the contact force, exactly. Normal reaction force or the contact force, it acts upwards. But remember, since it is passing through the pivot, will there be any moment? The moment is gonna be
No.
zero.
No.
Yes, okay. And if this moment is zero, and the plank has some weight, okay, the weight of the plank acts downwards. And let's say I'm pulling this plank over here by some string, okay, and that string has some tension in it. Okay, that string is attached to a pulley over here, and that pulley is attached to some weight, okay, and that weight provides the tension. Okay, now if I were to apply the first condition of equilibrium, so for the first condition of equilibrium, the sum of all forces must be zero, okay, and if the sum of all forces must be zero, then which forces must equal each other out, must be equal to one another? The weight and the tension must be equal to each other. But what about the normal reaction force?
It's already zero.
No, that's the tricky part. The moment is zero, but the force still is there. The force is non-zero. Okay, so the forces which act upwards, you're gonna add them and equate them to the weight. If this condition is satisfied, the first condition of equilibrium is satisfied. Okay, this was a tricky part. Okay, and this is where most of the students actually they mess up. Okay, they forget about this new normal reaction force. Anyways, so on. Now is it clear? What's the role of the normal reaction force? Okay, and now what about the second condition of equilibrium? So for second condition of equilibrium, will we consider the normal reaction force? Will we consider normal reaction force?
No.
Yes. Okay. No. Yes. Correct. No, because the moment is zero. So we are going to take the clockwise moment of the weight and the anti-clockwise moment of the tension. If both of them are equal, in that case, it's satisfied. So for example, if this distance is small d and that distance is capital D, actually that distance over here, this capital D, then the two moments is going to be weight multiplied by small d must equal the tension multiplied by the capital D. Okay. So the second condition of equilibrium must also be satisfied this way. All right. So now let's move on. Any question up till here?
No, sir.
No.
Okay. Now, guys, a special pair of forces called the couple forces, which produce a moment that's called torque of a couple. Okay, what is a couple? All right, guys, couple is actually a pair of forces. Now, if I have this weight over, this plank over here, again, just a moment.
Yes.
All right. Okay, couple. Now, if I have a, okay, let me resume. Okay, it's resumed. Okay, now if I have a plank, ignore that. I have a plank over here, and there are two forces. Okay, one acts at this end. Okay, and it's pivoted at the center. Okay, it's pivoted at the center. One force acts downward. Okay, and has a magnitude of F. And if the other force acts upwards, okay, you can make it here or you can make it down here, okay, but in the upward direction, and has the same magnitude F. If I were to extend them, this is the line of action of this force and this is the line of action of this force over here. Their distances from the pivot are the same, okay. This pivot, this force has a distance of d, and this force also has a perpendicular distance of d. Okay, and if I were to calculate the total moment which is created by these two forces, or the total torque which is created by these two forces, so how can we calculate that? Both of them are actually producing counterclockwise moments, right? This one is acting downwards, okay, counterclockwise. This one is acting upward, again counterclockwise. So now the moment due to this force is going to be force multiplied by D, okay, plus force multiplied by D again, because both of them are acting in the same direction. The total torque is going to be 2FD, twice of FD, right?
Yes.
Now such forces which have exactly the same magnitude, opposite directions, and act along different line of actions. Okay, I'm repeating what I just said. This is very important, guys. Forces which have the same magnitude, these are the three properties that must be present in these forces. Same magnitudes, okay, or magnitude, opposite direction, exactly opposite direction, okay, the direction is opposite, and are acting along different lines of actions.
Sir,
Force.
can you please explain the third part? The third point.
Acting along different lines of actions of force. I'm going to explain all three again, just a moment. Forces which have the same magnitude means F and F, okay, their magnitudes are the same. Opposite directions, one is acting upward, other is acting downward, and acting along different lines of actions of forces. I told you that this dotted line is the line of action of this force, okay, the line along which the force is acting. This is called the line of action of force. And this force over here, the force to the left, the dotted line over here represents the line of action of the force to the left. These two lines of actions are different, right? They are not exactly the same. They are different. So any two forces which have all these three components, all these three properties, they are called coupled forces. Just a moment, guys.
Yes.
Let me get this. Okay. They are called coupled forces.
And so like they should be 90-degree, right? Like the both forces.
They must be opposite to one
right?
another. Opposite, exactly opposite to one another. One acting downwards, other acting upwards. One acting to the left, other acting to the right. Okay, like this. And they must have some distance between them, perpendicular distance between them. Okay, not acting along different lines of actions of force. This implies that they are actually they have some distance between them, right? Now, the direct formula of calculating their torque, the torque of these couples is taking the magnitude of one of these two forces, okay, this F, multiplied by the perpendicular distance between these two forces. What's the perpendicular distance between these two forces? Is it 2D? Right?
Yes.
Multiply it with 2D, and what do you get? You get 2FD. And is it exactly identical to the initial 2FD which we calculated using the conventional method? They're the same, right?
Yes.
So this is how you could calculate the torque of a couple. By just multiplying the magnitude of one of the two forces by the perpendicular distance between these two forces. Okay? And guys, the definition of a couple force and the definition of torque of a couple are asked in the past papers. So I'll write them down in words over here, and you guys need to learn them. Okay. First of all, what is a couple? You just need to add up all those 3 points. Okay. So a pair of forces
with same magnitude of force and
having the same magnitude. Opposite direction.
And the same line of action.
Different lines of actions.
Yeah, different line of action.
Opposite directions and acting along different lines of actions of forces. These are called couple forces. And the second definition that is usually asked in the past papers, define torque of a couple. So this is pretty similar to the definition of a moment, okay? So the product of one of the couple forces okay, not both the forces, okay, product of one of the couple forces means the magnitude of one couple force, okay, not both the not 2F, just F, okay, just only one couple forces, and the perpendicular distance between the two forces, or between the lines of actions of the two forces, okay. This is not the perpendicular distance between from the pivot, okay, remember that. This is the distinction between the two, that this is the perpendicular distance between the two forces, perpendicular distance between the two forces, okay. Now guys, these are the two definitions which are asked for 2 marks or sometimes 3 marks as well, okay. And this is all about the torque of a couple now and couple forces. Now let me ask you guys a question over here. Pretty simple though. Are couple forces in equilibrium? These are couple forces, right? Are they in equilibrium or not? Any suggestion? Do they fulfill the first condition of equilibrium? Do they satisfy the first condition of equilibrium?
Yes. Forces are balanced.
Yes, the forces are balanced.
Yes.
Okay. The net force is 0. What about the net torque? What about the net torque? Do they have a torque or not? We defined the torque of a moment, torque of a couple over here. Yes, they definitely have a torque. Okay.
They have a
torque 0. The torque is not 0 now. Net torque is not 0. So if the net torque is not 0, then again it's not in equilibrium. Okay.
Yes.
And if this force didn't act along different lines of action, but acted at the same line of action in the opposite direction, then in that case, what would happen? Will there be any moment generated then? What will happen to this distance? If I take the force from here, I pick it up and place it over here in the opposite direction to the other couple force, what will happen to the value of this distance? Will it increase or decrease or become 0?
0.
Yes, it will become 0. And if it becomes 0, then these two forces are balanced out. The net torque will also become 0 in that case.
In that case,
the net torque becomes 0. Then these two forces are no longer couple forces. Okay, they are no longer couple. Couple forces are only those forces that have a certain value, a certain non-zero value of this D. Okay, the two forces which are acting in the opposite direction, they are not couple forces. So now the net torque is 0, the F net is 0. So now can I say that this object is in equilibrium?
Yes.
Yes, now it's perfectly in equilibrium. Right. Now coming towards center of gravity. Okay, but I just told you, I told you about the center of gravity in the beginning. I'll just go over it one more time. Center of gravity. Okay, this is actually an imaginary point. Okay, this is not an actual point. This is an imaginary point. Okay, a point in a body where all the weight, a point where all the weight appears to act. And it has been asked in the past papers one or two times to define the center of gravity as well. So this is the simplest definition of center of gravity. And I think this is enough because the definition was 1 mark, I think. So the point on a body where all the weight of the body appears to act. It appears, okay? appears to act.
Okay.
And I told you in case of a uniform plank, it acts at exactly the geometrical center.
Center.
Yes. Now, what about non-uniform masses? Non-uniform masses, for example, if I have a mass like this, okay, and it has a greater mass to the right and a lesser mass to the left. So in this case, where will its weight act from? So basically, center of gravity, as I told you, is the point where the weight acts from, okay, or where the weight appears to act. The side which has the greater mass, the center of gravity, it shifts from the center to that side, okay. So now you can take any random point over here, but like it should be in this region only, and that point can be marked as the center of gravity, okay. And this is the point from where the weight will now act in case of non-uniform bodies, okay. It does not, in case of non-uniform objects, the weight does not act from the geometrical center, but rather it tends to shift towards that side where the weight is already appears to be in a greater quantity, okay.
Okay.
And sometimes examiner asks you to label the center of gravity, okay, not accurately but just roughly. So this is how you're going to label it. Just label that point of that body which already has greater mass. Now, okay, now going on, now the last part of our discussion, a bit more about equilibrium and its forces, okay.
Yes.
Actually, this is a bit of extension of the first condition of equilibrium of forces, okay. Now, if you guys know what coplanar forces are, coplanar forces are basically those forces which act along the same plane, okay.
Along the same line.
The same plane. So for example, if I have the xy plane, x and y axis, this is an imaginary two-dimensional plane, okay, and it's called the xy plane. So if two forces, they act along the same planes, they are called coplanar forces, okay, if they act in the same xy plane. Now, a bit about the triangle of forces and triangle of forces for equilibrium. Now, you guys, I'm assuming you guys know from O-levels what head-to-tail rule was of vector addition.
Yeah.
I'll review it. Okay, head-to-tail rule. Okay, so if two forces are acting at a certain point, okay, for example, this is a point and one force acts over here in some random direction, and the other force acts in some other direction, okay, over here, for example. And if I were to calculate the resultant of these two forces, so how will I do that? Well, it's pretty simple. You just add them by head-to-tail rule, okay. You take the first vector, any of the two vectors is taken, okay. On the head of that vector, you add the tail of the second vector, okay. You add the tail of the second vector, and then you draw out a resultant force which starts from the tail of the first vector and goes till the head of the second vector, and this is the resultant vector. This is what the head-to-tail rule was, which you guys have done since O-levels, okay. Now this is called a vector triangle. For forces which are in equilibrium, a closed figure is formed, a closed triangle is formed, a closed triangle is made, and in that closed triangle, all the forces are actually acting in the same directions, and all the forces act in the same direction. I'll explain what
It's
this
not
means.
like the resultant is on opposite side.
Yes, exactly. It's actually, in this case, we have a resultant, right? In the other
Yes.
direction. In case of equilibrium, is a third force which acts in the opposite side direction to the resultant, right?
Okay.
So if I were to place this force over here in place of the resultant, so do we get a closed triangle? Do we get a closed triangle in which all the forces are actually acting in the same direction? Okay,
Yeah.
they are actually going in the same direction. 1, 2, and 3. Okay, head to tail, tail to head, 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 tail to head. Okay, they are actually
Yeah.
following the same path. So whenever we get an equilibrium triangle like this, in that case, that triangle is always for an equilibrium, for a body in equilibrium. Okay, and for
Yes.
bodies not in equilibrium, a resultant exists. Should I repeat this part, or did you guys get it?
I got it, sir.
So you can repeat it, please.
All right, I'll repeat it. Basically, if you have two forces, you add them by head to tail, right? If you add them by head to tail, you get a resultant like this. Now, if you consider this triangle over here, these two forces are acting in the same direction, but this force is not acting in the same direction. The resultant is not acting in the same direction, but rather it's acting in the different direction. Basically, if I were to trace, or if I were to follow this path, so I can go in this direction, then I can go up, but I cannot go back on the left hand side because now this arrow is pointing upwards. So I'll have to go upwards, right? This is what the arrow is telling me. But in case of, this is the case when the body is not in equilibrium. Okay, you got it till here?
Yeah, yes, sir.
Okay, and now if the body is in equilibrium, so what do we need to do in equilibrium? The forces must balance out, right? This resultant force must be balanced out by some external force which act in the opposite direction to this resultant force. Okay, this external force acts in the opposite direction to this resultant force and it cancels it out. Okay, and since it cancels it out, if I were to place this resultant force in place of this blue arrow, I would get a closed triangle. I would still get a closed triangle. And now, if I were to trace the path, I would go in the same direction. I can go up from here, okay? And now from here, I can go down because the arrow is pointing there. And I can reach back at the point from where I started. So whenever you get a triangle in which the arrows are pointing in the same direction, that triangle is for
equilibrium.
For a body in equilibrium. Now, do you get it? Or should I repeat?
Yes, sir. I got it.
All right, cool. Now, guys, another way of identifying forces in equilibrium, and guys, this is a very important way because this is how you're going to do your MCQs. Okay. Sometimes in the MCQs, what the examiner does is he gives you 2 to 3 forces, okay, and asks you whether the forces are in equilibrium or not. So now, for example, this is a point, okay. One force acts to the right, other force acts upwards, another force acts downwards. And now, this is just a diagram that the examiner gave you. Okay, this is a force F, this is the force T, this is the force W. Okay, and now another diagram in which W is acting over here. Okay, T is still acting to the right, but force F is actually passing from the side. It's not passing through the same common point like in this case. Okay, there is no common point from where the forces are passing. Now, what's the difference between these two? Difference between these two is that in the diagram to the left, now in the diagram to the left, we have the 3 forces which are originating or which are meeting at a common point, but in the diagram to the right, we have the same 3 forces. Actually, these are different 3 forces, but they are acting along different lines of actions, and so they are not meeting at a common point. Such forces that meet at a common point are known as concurrent forces. Concurrent forces. And whenever forces are concurrent, these forces are in equilibrium. Okay, so this is another way of identifying a body in equilibrium. We are going to extend the lines of actions of these forces, Okay, extend the lines of actions of the forces and see whether their lines of actions they meet at a common point or not. If they meet at a common point, then they are called concurrent forces, and those forces are in equilibrium. Okay, and MCQ will have 4 options. Okay, and in those 4 options, you'll have to use a ruler, you'll have to use a scale. Okay, and you'll have to extend out these forces and see whether they meet at a common point or not. The option which will meet at the common point, that will be your answer. That will be the answer to whether that system is in equilibrium or not. Guys, is it clear, or should I repeat?
No, it's clear.
Yes, sir, clear.
All right, cool. So these are concurrent forces. And yes, this was the last part of the lecture. Okay, we are done.